Hello and welcome to lecture 17 of Data 102. The topic of today's lecture is concentration inequalities. And this is going to be perhaps the most mathematical topic in this entire course. So why concentration inequalities are important may not be so apparent in today's lecture, but they're going to be used in the next unit on bandits. Okay, and it actually does turn out that concentration inequalities will show up almost everywhere in modern statistics and machine learning theory. Okay, so they are surprisingly very fundamental, and so whatever you learn today is going to come in, is definitely going to come in useful, whether or not it seems to be the case today. All right, so here's the plan. So first, we're going to say what concentration inequalities are and also give some motivation about why we should care about them. And then we're going to do a review of Markov's inequality. Okay, so it turns out that Markov's inequality is going to be behind many of these concentration inequalities, and in fact, behind all of the inequalities that we talk about in today's lecture. Okay, and then we're going to talk about Chebyshev's inequality, okay, which is a bound for utility probability using the variance. And then we will have generalizations of Chebyshev's inequality using higher moments. Okay, and then we're going to shift gears and talk about an entirely different method, which is this so-called Chernov's method, which makes use not of moments, but instead of this moment generating function. Okay, and this method turns out to be very fruitful. And so we're going to first do a proof of concept and apply this to Gaussian random variables where we can compute everything. And then we're going to really give a real application of Chernoff, which is to bounded random variables. Okay, so bounded random variables are those that have values between two finite numbers. Okay, and then we're going to make a very abstract definition. So we're going to define what is called sub-Gaussian random variables, and this is going to be a very useful notion. It turns out to be very useful. And I'm not quite sure if you're going to use this notion in the unit of bandits, but this has been very fruitful for the development of modern statistics and machine learning theory, and this notion is really used everywhere. Okay, so that's the plan for today. So now let's start with some motivation. So what are concentration inequalities and why should we care about them? Okay, so first a definition. So given a random variable, so I'm going to write random variable many times today, so I'm just going to use RV for short to denote random variable. Okay, so given a random variable x, the concentration inequality for x is an inequality of the form. Okay, so you want to bound the probability of x being you want to bound the difference between x and some number mu being bigger than some threshold t by some probability delta. And mu over here, okay, so mu cannot be, it can be any number, but usually we want mu to be either the mean or the median of x. Okay, and t is a deviation threshold. Okay, so it's going to give you a window, and we want to say that x is going to lie within this window around mu most of the time. Okay, and this delta value measures the the mass of the distribution that lies outside this window. Okay, so let me draw a picture to illustrate what I mean. Okay, so this is the real line, and suppose this is the mean mu. Okay, then my distribution x perhaps looks like this. Okay, so I'm not drawing so well. Okay, so fortunately this is not symmetric. And then t is going to be something that looks like this. Okay, so this is mu minus t. This is mu plus t. Okay, and then we want to consider this area. Oops. And this area here. Okay, and what the concentration inequality here is telling you is that this means that the shaded area is less than delta. Okay, and so that's what this inequality is telling you. And this is actually a two-sided concentration inequality in the sense that we want to bound the probability that x is distance t away from mu in either direction. But sometimes you may also be interested in one-sided inequalities. Okay, so one-sided inequalities are of the form. Okay, so probability x minus mu being bigger than t, less than delta. Okay, so this would be a right-sided inequality. And then we can also have a left-sided inequality, which is that x, probability of x minus mu being less than minus t is less than delta. Okay, so now that we know what concentration inequalities are, we need to talk about why we want so why we are interested in them, and also how to compute them. Okay, so now suppose x were a very well-known random variable, like a Gaussian, binomial, Poisson, okay, or any other random variable that you've seen in some previous probability classes. Then we actually know the density function and the CDF of these random variables exactly. And so when you want to compute a concentration inequality like this one, then it's sort of trivial to compute this because we can just go to the CDF and plug in the value of t, right? Or we may have to do some manipulation, take a 1 is the CDF or something like that, but it's still very easy. And then we can just exactly compute what this tail probability is. Okay, so then we don't need to do any work at all to compute a concentration inequality. Okay, so that's nice, but in practice, a lot of the random variables that we work with are not some of these well-known random variables. Okay, so they arise in the course of analyzing some algorithm as one of the intermediate values, or you might just have some relatively complicated output where you combine randomness of different sources. Okay, in that case, you don't know exactly what the distribution is, and so there's just no way to compute it, and it's not using like some one of the standard packages like the stats package in Python. And if that's the case, maybe we cannot hope to compute things on the dot, but we want to get bounds. Okay, and that's the ideal concentration inequalities, where we have some very general techniques where we can get bounds on these tail probabilities. Okay, so these are all called tail probabilities. using very few assumptions about what the random variable is. Okay, so this gives you a very flexible method for getting tailored inequalities. Okay, so now why? So I sort of told you a bit about the how. So now the why. Okay, so many reasons. I'm just going to list a few over here. Okay, so first reason, many algorithms nowadays are randomized algorithms. Okay, so for instance, a lot of search algorithms are randomized, and there's a reason why we randomize them, which is to get around certain adversarial situations. But there's a price to pay, which is that we don't really know. So usually in computer science, we want to make sure our algorithms run fast. And so we are interested in the running time or the time complexity of these algorithms. And if the algorithms are random, then this becomes a random quantity, right? And we want to say not just an expectation, but with high probability, okay, meaning you want some tail probability, okay? And you want the tail probability, you want some sort of upper tail probability on the running time. Okay, so we want to be able to obtain concentration inequalities for running times. Okay, and this is about running times. Other times, okay, so here's a very specific example of a randomized algorithm. And this is going to be dimension reduction. So dimension reduction is very important in machine learning because of big data. Okay, if dimension is too big, then it's very expensive to work. It's very computationally expensive to work with the data. So we want to do dimension reduction. And one big idea is to use random projections. Okay, so you randomly project the data onto a lower dimensional subspace. And so this is randomized. And sometimes it's going to work, and other times it's not going to work. And so we need to use concentration inequalities. Okay, so we need to use these inequalities to guarantee that this works. Okay, so now for something more classical. So now suppose you're back in statistics world and we want to do estimation. And suppose we are estimating mu. Okay, so either the mean or the median. Then concentration inequalities. Okay, so if you look at them, you stare at them for minutes, you see that they're exactly the same as confidence intervals. And in fact, what they give us are exactly valid confidence intervals for mu. Okay, and if you recall the lecture about, or the video about confidence intervals, credible intervals, etc. Okay, so there's this notion of exact validity versus asymptotic validity. Okay, and valid means that your confidence interval, if you say your confidence interval has 95% coverage, then it actually does have 95% coverage. Okay, but the problem is that a lot of confidence intervals that we construct are only asymptotically valid, okay, because they rely on something like the central limit theorem or normal approximation. And so this means that this 95% coverage is only achieved in the limit of infinitely many samples. Okay, so as opposed to this, exactly valid means that even with a fixed finite number of samples, the coverage guarantee is also or I should say, even with a finite number of samples, the confidence interval has the coverage that it as that it says it has. Okay, and this is something that concentration inequalities is going to give you. Okay, so last reason, and this is about bandits. Okay, so we're going to learn about bandit algorithms in the next lecture. And so it turns out that these make use of confidence inequalities to make decisions. And these confidence inequalities are produced using concentration inequalities. Okay, so there are many uses. I only listed 4 here. They have many, many more uses. Okay, so now we're going to do a refresher about Markov's inequality. Okay, so as I said in the introduction video, a large number of concentration inequalities are based on Markov's inequality. Okay, so this is the foundation on which we are doing all of our theory. And so it's very important to understand at the deep level what Markov's inequality is about and why it works. Okay, so what is inequality? So I'm just going to state it. Okay, so let Z be a non-negative random variable, then for any value, so any threshold t bigger than 0, we have the inequality where we bound the probability that z is bigger than t, the threshold t, by the value exponential of z divided by t. Okay, and it's crucial here that z is non-negative. Okay, if z can take negative values, this is not going to work. Okay, so let's do a quick proof. Okay, so the above is equivalent to if I multiply it both sides by t. Okay. And now let's look at what the two sides are. So the right-hand side, okay, so this is exponential of z. And I can write this out as follows. Okay, so by definition, this is integral of z from 0 to infinity times the density. Okay, so this is the right-hand side. Now, how about the left-hand side? Okay, so this is t times probability that z is bigger than t. And now I want to expand this probability in terms of the integral. Okay, and this is simply going to be the integral from, from t to infinity of pz dz. Okay, but then now I can rewrite this as t times the integral from 0 to infinity of an indicator that z is bigger than t, pz dz. And then I can move the t to the inside. And so now I see two things. Okay, so the right-hand side is integral of this function z. The integral of the left-hand side, the left-hand side is the integral of the function t times indicator of z bigger than or equal to t. Okay, in both cases, we weight them by this density p of z. Okay, but it's the same density, so we don't need to care about it. But we have that no matter what value of t it is, this function is always less than the function z. Okay, as a function of z. And in fact, okay, so we can draw a picture. Okay, the function f of z is equal to z, looks like this, right? And then the function on the left-hand side, okay, let's do it in blue. It's going to look like this. Okay, where this is going to be t, the value t. And so now this is always going to hold. And so the left-hand side is going to be this area, right, weighted by the density P of z. And then the right-hand side is going to be the area under the 45-degree line. And so this means that the right-hand side is always going to be bigger than or equal to the left-hand side. Okay, so that's Markov's inequality. Now let's move to Chebyshev's inequality. As well as generalizations of Chebyshev. Which makes use of the higher moments of a random variable. So let's state Chebyshev's inequality. Okay, so it says that for any random variable z, with mean mu and variance sigma squared, then for any t bigger than 0, okay, so we can bound the probability of z being a distance t away from mu by the value variance of z divided by t squared. Okay, so let's do a quick proof of this. And the proof is to apply Markov's inequality to a random variable that is not z, but is constructed out of z. Okay, and let's call this y. And y is going to be z minus mu squared. Okay, and now we see that this y is going to satisfy the assumptions of Markov's inequality in the sense that this is going to be a non-negative random variable. Okay, so that's the idea. Okay, now let's put it into action. So we started the left-hand side of the above. And now we have to transform it so that we obtain our value of y. Okay, so how do we do that? We just square both sides. Okay, and so this t squared on the right-hand side is going to be the value of t that we plug into Markov. Okay, so maybe if this is confusing to you, you might just want to rename this value of t to something else. Okay. And so now we plug this into Markov, and we get on the right-hand side expectation of z minus mu squared. Okay, so this is going to be the expectation of y. And then we're going to divide this by t in Markov, but now we've set t in Markov's inequality to be t squared here. Okay, so we have to divide by t squared. Okay, now we're done because the numerator is just the variance of z. Okay, so that's the definition. All right, so now let's apply Chebyshev's inequality to an important example. And this is where we set z a variable of interest to be the average of and ID so NID instantiations of some random variable zi. Okay, so z1 to zn are ID with mean mu and variance sigma squared. Okay, so what happens in this case? Okay, then if I compute the variance of z, okay, so just writing out what it is. Okay, so let's compute this. Okay, so the 1 over n goes to the outside as 1 over n squared term. And now I'm computing the variance of sum. If you were to expand this out, you would get some variance terms and some covariance terms. But because everything is independent, the covariance terms are all equal to 0. And so I can pull the sum to the outside. Okay, so this is 1 over n squared times sum from 1 to n of variance of zi. But now the zi's all have the same distribution. Okay, so this is just going to be 1 over n squared times n times the variance of one of them. And the variance of one of these random variables is going to be sigma squared, okay? Because that is how we defined it. And so after doing some cancellations, this is going to be sigma squared divided by n. Okay, and now we apply Chebyshev's inequality, and we get that probability that z minus mu is bigger than t is less than the variance of z divided by t squared. Okay, but now the variance is going to be sigma squared divided by n. And so all in all, the tail probability is sigma squared divided by n times t squared. Okay, so this example is very important. Okay, so we're going to see that in many cases, we want to get a tail probability for the sample mean. Okay, so this is what Chebyshev gave us. And recall the idea was to use Markov's inequality with this transformed random variable y that we got from taking the square of the difference between z and mu. Okay, but why do we have to take the square? Okay, so there's no real reason. We could have performed the same argument by taking y to be the 4th power, the 6th power, so on and so forth. Okay, and notice I'm using even powers because for odd powers, there's a problem. Okay, because for Markov, we have to have a non-negative random variable. Okay, so if you want to use odd powers, then we have to take an absolute value before we take the odd power. Okay, but let me just write this down. So for higher moments, what can you do? Okay, so for k being bigger than, well, k, any integer, 1, 2, 3, so on and so forth, applying the exact same arguments, but by taking the k power and not the square, we can bound this tail probability by z minus mu, expectation of z minus mu, absolute value to the k, divided by t to the k. Okay, so exact same argument. Okay, so now the question is, we have so many values, we have this bound for any k. Okay, so the random variable z has not changed, still the same random variable, but the quantity on the right-hand side, the bound has changed. Okay, so we have an entire family of bounds, one for every value of k, And the question is, which one do we choose? Okay, so are there drawbacks to choosing k is equal to 2 over k is equal to 4 or vice versa? Okay, and so actually it's not clear. So for different random variables z, different values of k, and okay, so for different random variables z and different values of the threshold t, you may want to choose a different value of k as the optimal k. Okay, so all of this really depends on those two parameters. Okay, so there's one problem. Another problem is that how do you even compute the kth moment of z, k of z minus mu, especially when you have this absolute value. And especially in this important example where z was equal to this sample mean. Okay, if you want to compute the kth power of this, then you're going to go bananas because you have to do this expansion in terms of kth power of this sum. Okay, and then it's just absolutely crazy. Okay, so it's just not really so convenient. So we're going to turn to another method, and so this method is called Chernov's method. And instead of using moments, it's going to use the moment generating function that combines all of the moments in a very nice way, so that it's very easy to, in some ways, it's very easy to select the optimal k. We now turn to Chernov's method, which makes use of the moment generating function. And so we need to start by introducing what this moment generating function actually is. Okay, so it all starts with the exponential function e to the z. Okay, and if you recall your calculus class, we have a Taylor expansion of this function. Okay, and it has perhaps the simplest Taylor expansion ever. Okay, so it's 1 plus z squared over 2 plus z cubed over 3 factorial plus z to the 4 over 4 factorial, and so on and so forth. Okay, so it's the sum over n from 0 to infinity of z to the n divided by n factorial. And so if z is a random variable, then if you take the exponential of some, okay, so maybe let's just do exponential z, and then take the expectation of it, then you might expect to get the same Taylor expansion, but replacing each of the terms z to the k with expectation of z to the k. Okay, so the power goes on the n side of the expectation. Okay, so what does the power go on the n side? Okay, you can think of this as exponentiating the random variable first and taking the expectation afterwards. Okay, and then we use additivity of the expectation to put the expectation around each term by itself. Okay, so this doesn't always, okay, so this series over here now is just formal, so this is like a formal series, okay, but it doesn't always converge. And in fact, it's not even well defined because for some values, some random variable z, certain moments may not even exist. Okay, so if you know what a Cauchy distribution is, a Cauchy distribution does not have finite variance, and all moments are higher than 2 are also infinite. Okay, so such an expansion only holds for certain random variables. And in the same way, the left-hand side, this definition of exponential of z, exponential z need not be finite. except for certain random variables. Okay, but the good news is that almost all the random variables that we work with on an everyday basis are nice enough so that we can often compute what the moment generating function is. Okay, so I'm just going to say that this doesn't always converge unless z is nice enough. Okay, nice enough just means that the tails of z's are not too heavy. Okay, so now we can define what the moment generating function is. Okay, so the moment generating function and this is often contracted to just MGF of random variable z is defined by, okay, so first is usually denoted mz of lambda. Okay, so this is going to be a function of lambda. And I just want to say that in this course, we're going to use this notation, m sub z, where z is the random variable in question. Okay, so sometimes people also like to use phi of z, sorry, phi of lambda. Okay, so this is also pretty common. Okay, so if you see people use the moment generating function elsewhere, they might use other forms of notation. All right, so let's just define what this is. This is going to be explanation of exponential lambda times z. Okay, so the only difference between this and the expansion we had before was that now I multiply our random variable z with some scalar lambda. Okay, and now this is going to be a function of lambda. Okay, so if it converges, so let me write this as a remark. If the right-hand side converges, then the moment generating function is going to be equal to the Taylor series, okay, 1 plus lambda z plus lambda squared explanation of z squared on 2 factorial plus lambda cubed explanation z cubed 3 factorial, and then so on and so forth. Okay, so the closed form formula is that this is going to be equal to the sum from 0 to infinity of lambda to the nth explanation of the nth moment divided by n factorial. Okay, and this is sort of why this is called the moment generating function. Okay, the moments are going to be the coefficients of each of the nth powers of lambda in this sum. Okay, and the further fact, so you can show that if I differentiate, okay, so first, if I differentiate the moment generating function, set this to be equal to 0, I'm going to get E of z. If I differentiate this twice and set this to be 0, then I'm going to get the coefficient of lambda squared, but I need to multiply by 2 factorial because of what happens when I differentiate. Okay, so I'm just going to get z squared, and then I can keep going, right? And in general, if I take the kth derivative, set it to be 0, this is going to be the kth moment. Okay, so this is the reason why this is called the moment generating function. Let us now see how we can use the moment generating function in order to get tail bounds. And the whole idea is to combine this MGF with Markov's inequality. Okay, so recall, how do we get Chebyshev? We apply Markov's inequality to a transformation of Z. right? So we had to take the square of z minus mu. And something implicit there is that taking the square, so that function f of x is equal to x squared, is an increasing function. So it doesn't change the ordering of inequalities. And it so happens that if we apply the function g of z, okay, so let's apply the function g of z is equal to e to the lambda z to both sides, then this is also increasing, so it does not change the sign of the inequality. Okay, so we have this. And now we can apply Markov to the right-hand side. And then this means that I'm going to have this bound. Here's in the numerator, I have expectation of lambda z. And in the denominator, I have e to the lambda t. Okay, but the numerator is just going to be the MGF. Okay, so this is mz of lambda, and the denominator is still e to lambda t. Okay, and so this over here is called Chernov's method. Okay, Chernov's method is just using the MGF with Markov's inequality. Okay, so it's a very elegant and simple idea. But let's try to see, okay, let's try to really push this and see how to squeeze the most out of this method. So here we had a certain choice of lambda. We didn't say what lambda we chose. And so this is actually valid. This inequality is valid for any lambda. And if this is valid for any lambda, it's valid for the minimum, okay, the lambda that achieves the minimum of all of these bounds. Okay, so what we really have is that P of z being bigger than or equal to t is less than the minimum over all lambda bigger than or equal to 0. Okay, we still need the MGF to be finite. Okay, that's not always the case. But okay, so suppose it is, then it's going to yeah. So we can put this minimum over here on the right hand side. Okay, and then now we just have to optimize in terms of lambda, and this is sort of akin to lambda over here is sort of equivalent to the choice of the power, okay, when we want to use moment-based methods. But the benefit of using the MGF and this lambda parameter is that we can use calculus. We can use calculus to choose the optimal lambda. Okay, so now to make this concrete, we're going to apply Chernov's method to Gaussian random variables. Okay, and now we're going to see Chernov's method in action. Okay, so to start off, let X be a normal with mean mu and variance sigma squares. Okay, then I really wanted the centered version of this. So I'm going to set z to be equal to x minus mu. And this is going to be normal with mean 0 and variance sigma squared. And this is going to have, the z is going to have MGF, mz of lambda equal to e to the lambda squared, sigma squared divided by 2. Okay, so this is something that you can compute. So I'm going to leave this as an exercise. So perhaps this should be under discussion. Okay, but this is not too hard, and this is equality on the dots. Okay, so now that we have some computation for the moment generating function, we can plug this into Chernov's method. Okay, so in other words, we can plug it into this expression here. And I need to be careful about copying and pasting so that I don't get anything I don't want to get. Okay. So plugging this in over here, I get that this is equal to the minimum of a lambda of e to the lambda squared sigma squared divided by 2 minus lambda t. All right, and so how do I minimize this? Okay, so naively you want to just differentiate the entire expression, then there's something that's a little bit smarter, which is to realize that your exponential is an increasing function. So this means that, okay, so I'm going to change e to exponential for clarity. Okay, this means that the minimum of this entire expression is going to be the same as the exponential of the minimum of the exponents. Okay, and now we're in good shape because the expression that we want to minimize is a quadratic. Okay, and so to find the minimum of this, okay, we can use calculus, or we can just use the quadratic equation that you learned in high school. Okay, so we minimize the exponents using quadratic formula. Okay, and then what we're going to get is that the optimal lambda star, okay, so this is going to be the bottom of your parabola. Okay, so you can use a formula to show that this is t over sigma squared. And then, okay, so I'm going to call it exponent f of lambda. And now if I plug in lambda star into it, this is going to be minus t squared divided by 2 sigma squared. Okay, so I'm just using the formula b squared over 4a, I believe, or minus b squared over 4a. Okay, so here b is going to be minus t, okay, because that's the coefficient of the lambda term, and a is going to be sigma squared on 2. Okay, so you plug all these values in, you're going to get minus t squared over 2 sigma squared. Okay, so putting this back into our tailed bound, you're going to see that probability of z being bigger than or equal to t is less than exponential minus t squared over 2 sigma squared. And this gives you Chernov's bound for normal random variables. Okay, so now let's try to make some remarks about what we just did. Okay, so if we compare this to the Gaussian density, the Gaussian density had exactly the same exponent over here. Okay, so the only difference was that we had this 1 over 2 pi sigma squared, 1 over root 2 pi sigma squared on the outside that is not present here. And not only that, so that was the density, and here I want an expression for the tail probability. Okay, so this is definitely going to be pretty tight. So it's tight up to constants outside the exponential. And so that's not too bad. Okay, so that's one remark. But then another remark is that it seems to be a little bit overkill for normal random variables, right? Because if you want to compute the probability of z being bigger than t, you can just look at the normal CDF, and we know exactly what it is. We have Python functions to compute it. So there's no real reason why we should use Chernov's method to get a tail bound. Okay, and the answer is right. So that's indeed true. Okay, so this over here is really just a proof of concept of how to use Chernov's method, because for Gaussian random variables, we have a nice formula for what the MGF is. Okay, so we're now going to take the same method, exactly the same approach, and apply it to other random variables for which we don't actually know what the CDF is. Okay, so we're now going to take the same method, exactly the same approach, and apply it to other random variables for which we don't actually know what the CDF is. Okay, and that's going to be the topic of the next section, which is applying Chernov's method to bounded random variables. Okay, and the crown jewel in this application is the so-called Hoeffding's inequality. Okay, but actually, before I move on, I want to say that so we have notes for this topic of concentration inequalities, and the notes are a little bit more detailed than what I'm writing here in the lecture, and we're going to have some plots in the notes. Okay, so for the previous section, we had some plots to compare the Chernoff bound with the Chebyshev bound and the exact probability. So you get a sense, intuitive sense of what are these, all of these inequalities are doing. Okay, so I'm gonna let you refer to the notes for that. All right. So how do we apply Chernoff's method to bounded random variables? Okay, so first I need a definition. Okay, so we say that a random variable z is bounded between two values, a and b, if all the mass of the distribution lies between these two numbers. Okay, so z only takes values between a and b. Okay, and we also say that z is centered if the mean of z is equal to 0. Okay, so centered is nothing new. It's just a nice term to refer to this. And so this is going to be the class of random variables that we want to work with. And it's really broad, includes many things that we care about, such as Bernoulli random variables, uniform random variables between two numbers, beta distribution. Okay, but really the key is Bernoulli. So somehow Bernoulli random variables are just everywhere, and so we want to get bounds on sums of Bernoulli random variables. Okay, so what's the idea? The idea is that when we apply Chernoff's method to Gaussian random variables, we didn't actually really use anything about Gaussian random variables apart from one property. And that one property was a computation of the moment generating function. Okay, so let me just write down what I just said. So the only property of Gaussian random variables that we used in previous section was that the MGF had this nice formula. Okay, and so if it were the case that bounded random variables also had a nice formula for the moment generating function, then the exact same argument goes through. Okay, we don't have to change anything at all, and we get the same results. Okay, and that actually turns out to be the case. And that is the topic of, or that's the statement of Hoeffding's lemma. Okay, so Hoeffding was a mathematician. I kind of forget which country he's from. Okay, so he lived, I think, in the first half of the 20th century. Okay, so what does it say? So suppose that Z is bounded between A and B, and that Z is centered. Okay, so mean 0. Then the MGF of Z is bounded from above by exponential b minus a squared divided by 8 times lambda squared. All right, so we don't have an exact computation anymore, but we have an inequality. And this inequality is good enough. Okay, so proof of this exact bound. Okay, so this is actually the tightest possible bound. Okay, it turns out to be a little bit tricky. Okay, and so I'm gonna let you read about that on Wikipedia. Okay, but the proof is not necessary for our class. Okay, so this is just a little bit too complicated. Okay, but let's see how we can use this. Okay, so what does this imply? Okay, so this implies that we want to compare this to the e to the lambda squared, sigma squared bound that we had for the Gaussian MGF. And so if I do a substitution, right, so this is going to be equal to sigma squared lambda squared on 2 if I let sigma squared be equal to b minus a squared divided by 4, right? Okay, so now if I plug this value of sigma squared into our calculations in the previous section, okay, we're going to get something. Okay, so we can apply, so this implies we can replace sigma squared with b minus a squared divided by 4 in our previous calculations. And what do we get? Okay, so let's just copy it. Let's copy this, paste this here. And now I need to substitute back what sigma is. Okay, so this becomes 2b minus a squared, and then 4 goes in the numerator, right? Okay, but then I do a cancellation. Okay, so cancel 2, this becomes 2. Okay, so I'm just writing this out again. This becomes minus 2 t squared divided by b minus a squared. Okay. Okay, so this is what happens for a single bounded random variable. Okay, but what we are really interested in is sums of bounded random variables. And so what we want to do is to apply Charnot's method to a sample mean of that kind. And it's going to turn out to be very convenient. Okay, just as was the case for applying Chebyshev's method. Okay, and recall the reason why Chebyshev was so convenient for these sums was that we had this way to write the variance. Okay, so this was just equal to sigma squared divided by n. And so a very similar property is going to hold for moment generating functions. Okay, and so this is going to be the following lemma. Okay, so let me just write this as a lemma to denote it. Okay, so this lemma is going to say that the MGFs of independent random variables is multiplicative. Okay, so let x1, x2, xn be independent random variables. Let's set z to be equal to the sum. Okay, here I'm not going to normalize by 1 over n. Okay, for generality. So I'm just going to state this for the sum. Okay, and the statement is that the moment generating function of the sum is going to be equal to the product of the moment generating functions of each of the xi's. Okay, so what's the proof? Okay, so proof is just algebra in some sense. Okay, so m0 lambda is equal to, by definition, e to the lambda summation from 1 to n of the size. Okay, so you probably can really guess what we're going to do. Okay, so the sum is in the exponent. Okay, so we're going to use the fact that exponentials are multiplicative. So e to the a plus b is e to the a times e to the b until this becomes a product of e to the lambda xi. And now all of these are independent. So we're going to use the fact that for, okay, so as an aside, for yz independent, then e of yz is equal to e of y times e of z. Okay, it's the same if you have multiple, more than just two. If you have 3 independent random variables or more, okay, the expectation is just going to distribute. Okay, so you can put the product on the outside. And then now we notice that each of these terms is just the MGF. Okay, so each of these is just MGF of xi. Okay, and then we're done. All right, so now I want to combine this lemma with Hoeffding's lemma that we had slightly earlier. Okay, so where's Hoeffding's lemma? Okay, so here it is. So I want to combine these two lemmas to get a tailed bound for sums of bounded random variables. And that is going to be Hoeffding's inequality. Okay, so this is the crown jewel of the section. And just like Chernoff, this is an inequality that you find yourself using again and again and again. Okay, so let x1 to xn be independent random variables bounded between A and B, then probability that 1 over n times the sum from I is equal to 1 to n of xi minus expectation of xi. Okay, so I did not assume that the xi's are centered. Okay, this is to make this more general. Okay, but then when we sum of the terms, we need to subtract off the means of each of these. Okay, so I want to bound the probability that this sum is bigger than t. Okay, and this is going to be less than exponential minus 2 times n times t squared divided by b minus a squared. Okay, so same as in the one variable bound, but now I have a factor of n in the numerator and its exponent. Okay, and this is a one-sided bound. Sometimes you want a two-sided bound, and that's what we get. So furthermore, we have the two-sided bound. Okay, and I'm going to be lazy again and just copy and paste. So same thing. Copy, paste. Same thing, but with 2 small changes. Okay, so first change is that I need to take absolute values here. And then the second change is that I'm going to put a 2 in front of the exponent. Okay, so let's prove this. Okay, so let's first assume, without loss of generality, that each of these expectations is equal to 0. Okay, so we can do this by simply replacing xi with xi minus expectation if we need be, and just like relabeling things. Okay, this is just to make things more convenient. And now let's write z to be equal to the sum from 1 to n of xi divided by n. Okay, so this is now going to be the term inside the probability here. Okay, so it's the same thing now. But the reason why we wanted to write it this way is to make use of the previous two lemmas. Okay, so first thing we do is that we observe that this term is bounded between E over n and B over n. Okay, so this is going to come in useful later. Now we begin our string of equalities. Okay, so first we start with the MGF of Z, and we want to bound this. First, I use multiplicativity to write this as the product of each of the MGFs of each of the xi's. And now using this observation and using Hoeffding's lemma, I can bound this by, I can bound each term by exponential b minus, let's see, b minus 8 squared divided by 8 times lambda squared. Okay, and I think I forgot the n. Okay, so there should be an n squared here as well. Okay, that comes from the fact that the terms are not bounded between a of n and b of n. Okay, so this was by applying the second lemma. Sorry, okay, so first step was applying the second lemma. Second step was applying Hoeffding's lemma, the first one. And now I can put them together, so I can, now I can keep going. Okay, so now I see that each term is exactly the same. Okay, so there's no index I on the inside. Okay, so this means that the product of n copies of the same thing. So this is the same as one copy, but raised to the nth power times n. Okay, but now this is going to cancel with this in the denominator. And so I just get this. Okay, so just writing this out again. This is going to be b minus 8 squared divided by 8n times lambda squared. Okay, so what's my sigma squared now? Is sigma squared is going to be equal to b minus 8 squared divided by 4n. Okay, so now we apply Chernoff's method. Exactly the same argument. So again, I can copy and paste. So I hope it's wise to do that. Okay, let me scroll up again to see where my equation is. So here it is. Okay, so under the hood, we are using Markov and then optimizing a lambda. Okay, but because the logic is always the same, I can just say replace sigma squared with a new value of sigma squared. Okay, so now I'm going to have this b minus a squared. Okay, so there was still a 2 over here. But then in my numerator, I now have 4n, right? And so 2 is going to cancel with 4. Why is this not working? Okay, so at the end of the day, I get minus 2n t squared over b minus a squared. Okay, and then this is exactly the first statement in Hoeffding's inequality. Okay, how do we get the second statement? We have a bound on one side, and now we just need a bound on the other side. Okay, and to be more precise, okay, so let's do this a bit more carefully. So for the two-sided bound, what I want to do is to take this left-hand side and break it up into two parts. Okay, so this is going to be, okay, so if the absolute value is bigger than t, this means that either the non-absolute value portion is bigger than t, or it means that minus the quantity and the absolute value is bigger than t. Okay, so that's the definition of absolute value. And so we already bounded the first guy. Okay, so first part of Hoeffding's inequality is bounding this first term. The second term is exactly the same. So we run Hoeffding's inequality, but with this as z instead. Okay, so this is going to be the new random variable z. Okay, and then we get exactly the same bounds. Okay, so that concludes the proof of Hoeffding's inequality. All right. Okay, so that's fantastic. And in the lecture notes, we apply Hoeffding's inequality to get a tailed bound for the binomial distribution. Okay, and we had some computations, and then we also have some plots. Okay, but I'm going to refer you to the notes. And so I just want to end by talking about sub-Gaussian random variables. And I forget what should be the numbering now. I think it should be 7. Okay, so going up. In this last section, we're going to talk about going abstract, sub-Gaussian random variables. Okay, so this is going to be pretty short. The basic idea is that it's sometimes helpful to work at an abstract level. Okay, and why is that? Because when we do things abstractly, this helps us to make connections between different areas. Okay, and so we make connections and we can see how we may use tools that we develop in one setting and apply it to another setting. Okay, and Chernov's method was a very successful example of doing this. Okay, so originally it seemed like it was for special cases like bounded random variables, Gaussians, but now if we abstract this one property that we are using, which is that we have control over the moment generating function, then we could actually apply the same methods to a much broader class of random variables. Okay, so we're going to make this property into a definition. So here's the definition. So we say that a random variable x with mean mu is sigma sub-Gaussian. Okay, so sigma here is a parameter. Okay, so x is sigma sub-Gaussian if we have the bound of the MGF. Okay, so I want to center x, and the bound is going to be what we saw in the Gaussian case, e to the lambda squared sigma squared divided by 2. Okay, and whenever we have such a random variable, we get a Chernoff bound using Chernoff's methods because everything is formal. Okay, all we used was this bound on the MGF in the previous sections. Okay, so this is a very fruitful idea because it turns out that many random variables that turn up in practice are actually sub-Gaussian. Okay, so this holds for many settings, including statistics, machine learning, signal processing, numerical linear algebra, and others. Okay, so this was a very successful idea. In this video, we're going to consider a binomial random variable. Okay, and we're going to call it Z. And being a binomial, it is just going to be the sum of Bernoullis. Okay, so maybe more precisely, we're going to consider a binomial proportion. Okay, so X is going to be the binomial, And Z is going to be X normalized by N, where N is the total number of Bernoullis in this sum. Okay, and so now we want to apply Hofding's inequality to Z and also Chebyshev. We're going to compare this also to the true tail distribution, right? And we're going to see what we get. Okay, so first we're going to change the setup a little bit. And instead of looking of considering the probabilities for a fixed threshold T, okay, so recall this was the threshold window, we're going to use a proportion. Okay, so what we want to do is to bound the probability that X exceeds its mean mu by a C fraction. Okay, so maybe C is like 10%, 20%. Okay, but we want to think about this in terms of proportions. In order to get this probability on the right, okay, and apply our concentration inequalities to it, we need to massage this back into something that we are more familiar with, which is the Z minus P bigger than T. Okay, so we have to do these substitutions. Okay, so whatever C is, okay, so we need to choose T to be equal to C times P. Okay, where P was the probability of the Bernoulli. Okay, so I'm just going backwards. Then this is going to give you probability of X minus mu is bigger than N times T. Okay, so we also brought mu of X to the left-hand side. And now this is going to be, if I divide both sides by N, this is going to give me P of Z minus P being bigger than T. Okay, so now we apply Hofding's inequality. Let's see. Okay, so we don't actually, okay, so my bad. So we don't actually apply Chebyshev here. So first we're going to apply Hofding's inequality. We're also going to consider the exact tail probability using the binomial distribution. And then we're going to use normal approximation. Okay, so this is going to be a sample mean, right? So it's going to be it's going to converge to a normal by the central limit theorem. And so we can use normal approximation. Okay, so it's going to converge to a normal with mean N times P and variance N times P times 1 minus P. So whenever we think about confidence intervals, okay, oftentimes we use this sort of normal approximation to get the intervals. And so we want to compare the quality of the tail bounds for these three different methods. Okay, so here I ran some code already. Okay, so you can take a closer look at this code and the lecture notes. Okay, so I'm going to let you do this in your own time. And I'm just going to show you what the results are. Okay, so 3 curves over here. The exact tail probability is going to be given by the blue curve. And here on the x-axis, what we are varying is n. Okay, so we're going to keep the proportion fixed. Okay, the proportion is going to be 0.125, and we're going to let n increase. Okay, and the reason why you see this jagged behavior is because the binomial distribution is a discrete distribution, right? So as I increase n, then sometimes I include some values of k, and other times I'm not going to include other values of k. And so that's why I'm just doing this jumpy thing. Okay, but the blue jumpy curve is actually the exact tail probability. The red curve is going to be the normal approximation. Okay, and typically when we want to get a confidence interval, okay, so we're going to use this normal approximation, and you can see that we are overconfident, and for some values of n. Okay, so for some values of n, the bound that you get from using normal approximation is going to be an overconfidence. Okay, so it's going to be an underestimate of the true tail probability. Okay, that happens whenever the blue curve is above the red curve. Okay, so that's clearly a bad thing. And on the other hand, the bound that we get from using Hofding's inequality, the green curve always lies above the blue curve. Okay, so it's always going to be an upper bound. Okay, so is that sometimes the difference seems to be pretty big. Okay, so that's a price you pay for being safe. Okay, and safety is that it always lies above the blue curve. So the tail probability that's that's going to be the y value is always going to be bigger than the true tail probability. Okay, So in the lecture notes, we also have some writing about confidence intervals. Okay, I'm gonna let you read this in your own time. Okay, so here we want to compare different methods of getting confidence intervals and argue for why you might want to use concentration inequalities in some cases.